Finally, the last option within the Ouija menu is the slide projection. Pressing the Ouija menu key from the projections menu, we arrive at the dogleg menu, and then you press slide, and then you press edit, and then you press add, and we're going to add the last slide interval, which is from 1853 to 1866.5. You can see here all this, that the last 5 slide intervals are kept and they are discarded over to the top. So we press exit here to return to the slide projection menu, and we are going to go ahead and make a projection to bottom. The first input is the survey to bottom distance, which in this case is 19 meters. And the next input is the borehole geometric correction. For 8.5 holes is 1 meter. If you want to see more explanation about this borehole geometric correction, please check out the manual. Press enter. The estimated rotating build-up rate in this case is 0, but I am going to put in a value here of minus 0.2, so you see how this works. So minus 0.2, so the natural rotating drop-off rate is minus 0.2. And then we have the first result, which is the slide course length between the last 2 surveys is 11 meters. The calculated sliding dogleg is per 30 meters 8.88 at a tool face of 11.38. The estimated rotating build-up rate is minus 0.2. So I'm going to press continue here. I will say yes to recalculate the build-up rate, and we go here and I say that the calculated sliding dogleg change value to recalculate build-up rate. And so let's go to 8.36, which I calculated previously, and that's going to give me a rotating build-up rate, basically 0. I'll delete this number here and just press 0, and you press OK. And then this is the same thing now. Slide course length between the last 2 surveys 11 meters. Estimated sliding dogleg is 8.36. So you see, if the BHA was dropping slightly, then the calculated dogleg is larger, because you need a larger dogleg to counteract the dropping tendency of the BHA. And you say here recalculated rotating build-up rate is 0. And we continue, and we say no this time. And then there's 2.5 meter slide below the survey. Expected sliding dogleg is 8.36, and we leave it like it is. We're happy with that number. And the projected tool phase is the same as before, 11.37. You could change these values if you feel that below the survey your slides were more or less consistent and your tool phase was more to one side or the other. So you accept this, and we have here the result at bottom. So the slide course length survey to TD is 2.5 meters. The sliding DLS is 8.36, and the projected bottom is at 1882, inclination 67, azimuth 70.1. So I'm going to append this to the temporary projection file, which in this case is the first projection. So I'm going to create the projections file and insert this value in there. So now the projection is to the bottom of the hole. So we append, and we press option, and we press anti to see what the position of the hole is at the bottom of the hole and not at the surface. So we go anti, plan is still chosen from before, we press enter, OK. So here we see the comparison between the path of the plan and the path of the actual well at bottom. We see the situation is improved significantly. We are a little bit less to the left, and the inclination is less than the plan at this point. Earlier on, I had saved the projection from at the survey, and you can see this here by pressing the R key, and we see that before we were ahead in inclination and 3 degrees to the left, and now pressing any key will return us to the to the actual, and we see that at bottom we are actually less than the plan, which means we're going to catch up to the plan eventually. At this point, I want to explain to you what the numerical plotting routine does exactly. Basically, imagine that there is a plane which is perpendicular to the plan, and that plane is traveling down. Imagine a circle if it's easier for you. Circle which is perpendicular to the plan, and it's moving down to the through the plan, and it will move down until it's just touching the bottom of this last survey. In this case, it's the projection at bottom that we will be touching. So at that point, the actual well is at a certain distance to the left of the plan, and looking straight up, we can see how far above the plan the actual well is. This measurement is done in 3D, so it doesn't matter in which direction the hole is going and the plan, you will get the same distance above, below, left, or right. It is important to understand that this is a 3D projection, and because I've had a few people tell me that, well, yeah, they measure the distance from the plan to the survey, and it shows that's below the line, but my program here will show that's above the line. But it depends on the plane of proposal. As you rotate the plane of proposal, the actual well will seem to be either above, even below, left, or right. But actually, no matter which way you turn the plane of proposal, the well is exactly the same distance from the plan. To illustrate this further, look at the picture of the dancing girl. Imagine that the leg straight down is the plan and the leg stretched out is the actual well. And furthermore, imagine that the girl is not rotating, but basically the girl is stationary and you are going around and round and looking at her from different perspectives. You can see that depending on the perspective that you have of the girl or her legs, the actual well will seem to be either above, below, or actually right on top of the plan. But fact of the matter is that the well is a fixed amount above the plan, and Easydrill calculates it in this manner. So I hope this clears up some doubts. We return to the screen displaying the relative position of demo versus plan. And now I'm going to press the continue key because there's this other screen which before was not applicable, which compares also the curvatures of the two wells. So you can see that at the closest point between uh, demo and plan, the plan has 4.5 degrees build-up rate, and the well has 1.08, so we are generating only 24% of the required build-up rate, although we have other things to consider. And the walk, again, is the similar situation. The plan is going straight, and we have an actual walk. And also we compare the dog leg of the plan with the dog leg of the actual well and the tool face of the plan with respect to the tool face of the well. And so you can see that with this anti-collision numerical plotting routine, you can compare the two wells, or a well and a plan, with respect to position, with respect to angle, and also with respect to curvature. So this is an invaluable tool to follow 3D well.